back. So you're going to get a reflected energy, which is called as echo. So target or echo. So basic physics says that the range is going to be c times this round trip time by 2, because it's two-way travel, you have to divide by 2. Okay. Assuming that radio waves are propagating at the speed of light, which is approximately a valid assumption for all practical purpose. Now we'll define few things. Uh, First of all, there is a pulse. I told radars are going to transmit in pulses, and so it's going to have a pulse width. So this is the width of the pulse. Let us say tau. And this pulse keeps repeating at a particular rate. So that is called the pulse repetition time, or more colloquially, it's called as pulse repetition frequency, PRF, pulse repetition frequency. I was telling that they operate at 1 gigahertz and all those things, right? But how come it looks like a digital signal? See, this pulse repetition frequency will be, let us say, for a search radar, around 1000 hertz. Okay. So how do we say it's operating at 1 gigahertz? The transmitter or the radar is operating at 1 gigahertz. Looks contradictory, right? The PRF itself is 1000 hertz. How come that pulse becomes just can be anything? Open to the class, not only Sandita. So all radar books, they show the waveform like this, as if it's a digital signal. Sanjay?
Can you repeat the question, sir?
Yeah, see, when I talked about radar frequencies, I told that it works at 1 gigahertz for search radars and 8 gigahertz for tracking radars. Whereas this duration is just 1000 hertz. So where is this 8 gigahertz and 1 gigahertz and all coming?
Sir, carrier frequency.
Yeah, good. So it's actually when they're representing it like a pulse, it's nothing but during this pulse time, this carrier frequency is transmitted. Okay, so this can be anything, right? Whatever be the pulse width, you can still have this carrier frequency going in this. So it's actually if you strictly look at the representation, it's going to be like this. So within a pulse width, you're going to, or within the pulse, you're going to have this burst of carrier transmission. And then you stop it and then keep listening for the return echoes. Is this concept clear? Don't think that it's a digital signal. No way we can transmit a digital signal. It has to be some carrier signal. And that carrier is going to be in short bursts. Normal carrier in time is going to look like this continuously. Okay, goes on. But suppose I the same carrier, I send it for a brief interval, it becomes a pulse. Like this, I keep sending it. That's what radars do. Okay? So don't think that it's some high voltage pulse which is going into the atmosphere. So It is a EM propagation, and you require the carrier to do that job. Then there is another thing concept called as, whenever we talk about power in radar, we talk about the average power. That average power is nothing but peak power by pulse width. Some of them, that's why it's not generally represented as tau and PRT, or the complete time. Now, into the peak power. This sort of averaging out the, or finding the average, we did it in our embedded systems. Can you just tell me where we applied this concept of average? In that case, it was voltage. So there's nothing but peak into, let us say this is A, this duration, and this duration we'll call it as B. It is A by B. Higher the A, more is the average. So we use this concept somewhere in our embedded systems course also.
Balance with modulation, sir.
Yeah, correct, Sanjay. That is used for changing the speed of the motor. Remember, right? So, and I called it as duty cycle, if you remember. The same thing. Okay. Now the question is, it's open to the class. So I would like to have as much power as possible so that my range increases. Should I have a high pulse width or a low pulse width? So what I am asking is, should this A be high or low? Okay. Think about it. Let's see.
High.
Subsequent slides might answer that. You'll get an answer for it.
Or is it high?
Now, high. Okay, Sanjay is telling high. Okay, then someone should oppose that and say no, it should be low. And both should justify their answer.
Sir, if it's high, then there will be less average power wasted.
Okay, he says you like, if it is high, more the average power, better it is. Someone should defend that it should be low. I would like to have a low pulse width. Okay, maybe a few more slides. Okay, we'll just go back to the block diagram. So, when you talk about radar, there is a transmitter, some timing control, which is going to give the pulses in form of digital thing only. Okay, so you decide the pulse with tau and the pulse repetition frequency, and you transmit those pulsed waveform. So it goes, all that brute power goes out as a pulse. After that, you'll have to receive the signals. So some amount of signal comes back. So you have the reflected energy coming back, then goes to this. Now something interesting happens. Uh, there is a switch called as duplexer. Its function is whenever the transmitter is sending that high powered burst, it should protect the receiver. It should not happen that some amount of energy goes into the receiver directly. It's just going to burn out. Okay. So whenever the transmitter is on, the switch is in this position. The moment that burst is over, that is for a duration of tau, it is on. But after that, it switches back to the duplexer. Now, during the receiver side portion, this path is through this. Now, receiver will do all the signal processing and all those things and give it as a form of display, which is useful for the controller. So, the most critical you can say assembly or sub-assembly is this duplexer. God forbid it fails, then the entire receiver chain gets burnt out. Okay, because here you're talking about 1 gigawatts, and this poor fellow will just take 100 milliwatts maximum. You can just imagine what will happen when there is a malfunction of this duplex. And then we do all this display and all this stuff. Now, is it okay? This basic block diagram of the radar? Problem is, it's a common antenna. Okay, had it been two different antennas, no issues. Is it okay, Saru? Or you have some doubts?
Sir, can you repeat?
Yeah, no issues. Okay. First is screen. Okay. We discussed that this transmitter, transmitted pulse in a radar is going to be a pulsed one. So it keeps going on. The pulse width is tau, and the repetition frequency is pulse repetition frequency, PRF. Let us say we have started the transmission at t is equal to 0. Let this be t equal to 0. So this timing control is going to just switch on this transmitter for this particular duration tau. During this time, this high frequency burst is going to come out. It goes through the duplexer and then to the antenna. And function of the antenna is to increase the gain, and this goes and hits the target. Now, what's going to happen is after that there is no transmission. You're just listening. Okay. So at that point of time, whatever be the reflected, I'm talking about. Let's say this is on period and this is off period. During the off period, again this reflected energy comes and strikes the antenna. Through the antenna, it's routed to the duplexer. But now the duplexer has changed its position. It goes to the receive mode, and this RF energy goes to the receiver. And in receiver is same as what we have learned in the first module. It will be a heterodyne receiver, and it's going to give out some demodulated output, which goes into a signal processor. That signal processor, I'll tell you why it is required. Okay, and then you get the display. So if you know, you must be wondering, how do we get this plant position indicator? So at t is equal to 0, this electron beam scans like this, okay, from center to the periphery. So it scans like this. Wherever there is a target, you will get a blip. That is the received energy. Okay, it's all synchronized in time, so you get the blip. Now this distance will give you the range R. And angle is going to be the antenna itself is coupled mechanically, so you get theta. So that's how this raster is what makes the electron beam move from center to the edge. And during that time, if this receiver is going to give you some blips that appears as a target on the screen. That's how the entire thing works. Is it okay, Suru?
Yes, sir.
Then there are some displays which are called A displays and B displays and all this stuff, in which you don't have a circular display. Straight away you will be getting the range versus blip. These were initial days it was like that, but angle information was lost in those days. But presently it's just this one. Even a refined form of this in which you don't really require an electronic beam to move here and there. It just goes into your desktop. That's all nowadays. The displays are all desktops. So we don't have cathode ray tubes and all those things. Okay, now I have to make a decision. At this receiver, I am going to keep getting some signals because it is free space, some noise also is going to come. So in time, if you see, let us say we'll just concentrate on just one single pulse. So you are transmitted here. There is some lot of noises there, and finally you get a echo, which is the actual target, and then some noise like this. Okay. Now this receiver has to take a decision at what level it should say that it is a valid target or not. It should give a threshold. It should keep a threshold so that if the signal is greater than this threshold, it should declare it as a target. Okay, now let's go to the next slide. So this is what you see for a single pulse. This is time, and let us say this is the voltage, amplitude of the incoming signal, and it's going to be noisy. Okay, you don't know, you can't predict this, but here and there you're having some peaks. Now the question is, should I go for this VTH1 or VTH2? Just look at this slide. Threshold 1 is green color and threshold 2 is red color. And the black is the received waveform or signal in time. Okay. So, which one would you opt for? The first threshold 1 or threshold 2?
Sir, 1.
So, Sarup says 1. Anyone for 2? Why, Sarup, you want 1?
So because it eliminates other
Noise.
noise.
Okay, now someone should say that no, you want threshold 2. So, okay, I'll lead you to the correct answer. Sarup, what do you mean by noise? Okay, now you eliminated noise. You assume that this is the noise level because you have kept your threshold high at this point. So, you are telling you eliminated noise. What will noise, what will be the effect of such noise on the user?
Didn't get you, sir.
So you said that you're right. When you increase this threshold, you are eliminating noise, right? So how do you think it's benefiting the user? Finally the radar controller. Let us just draw one raster. Okay.
So instead of showing blip at only 3 positions, it will show at many positions.
Multiple positions, right? Good. So what shall we call it as? If in a defense radar, if the controller sees multiple blips, what happens? He'll panic, right? It's a alarm. So that's why it's called as false alarm. So instead of just getting three, this is what it looked like. Okay, for Sarup's threshold, this is what it will look like to the user. I'm just drawing it at 90 degrees. It can be at any angle, just to make things simpler. But suppose, let us say we are fixing it as threshold 2. The same display will look something different. Okay, so instead of seeing 3 blips, this fellow is going to see 6 blips. So you're going to get false alarms. So any argument against this? This looks like a very nice thing, right? You just increase the threshold. But will it create some problem? Suppose, let us say, extreme case, I'll keep the threshold here. Blue color line, okay? TH3. Then what happens?
It may not capture some of the weak signals. So.
Good. So we might miss out on weak signals like this fellow, though might be an actual aircraft, we might miss it. So it's always a compromise between threshold and false alarm. Like you want false alarm or you want to miss the targets. So this particular control is given to the user, the fighter controller. Okay, he has a knob in which he can adjust this threshold as per his convenience. But nowadays there are other techniques also by which automatically you can do this job. Is it clear now why this threshold is very important? Sarup, is it okay? If too higher a threshold, you will miss targets.
Yes, sir.
And
Sir, can't we have 2 thresholds?
any given time, you have to set it at one threshold, but you can vary the threshold continuously. Then it amounts to having 2 receivers, right?
Yes, sir.
That no one can afford. There is another big issue in radars that is called as range ambiguity. The range can be ambiguous. It happens because suppose between the PRT, see now in time in x-axis corresponds to range. Okay, in radar that is something you have to get used to. Time just translates to range. Now it so happens that there is a target at this particular time, then there is no issue. Let us say there is a display and this fellow will correctly get display. This target will appear like this. Uh, but let us assume that there is a target, this blue color one, which is beyond this interval capital T. Then what's going to happen is this pulse is gone. You get the first red color target. So it goes up to the edge of the display. Then the next pulse is transmitted. When the next pulse is transmitted, this blue gets displayed somewhere here. So this range, though it's much greater than the red one, gets displayed as if it is closer to the radar. So this is called as range ambiguity. This you can also calculate that you can simply this basic manipulation you can find out that it's nothing but C divided by 2 times PRF. So, like example, suppose PRF is 1250 hertz, which is generally for a search radar. Then you substitute here, you will get this range, unambiguous range as 120 kilometers. So, any target within 120 kilometers will be correctly represented on the scope or display. Anything beyond that will give an ambiguous range as if it's coming from a closer target. So now the question is, do I require a high PRF or a low PRF? High or low? Yuvan, can you just attempt this?
Sir?
Yeah, should I go for a high PRF or a low PRF?
Sir, don't know, sir.
No, looking at this slide, you tell me.
Sir, I can't see, sir. Okay.
You can see, right?
Yes, sir.
Yeah. Now tell me whether I should go for a high PRF or a low PRF.
For long range, sir.
For unambiguous range. I don't want any ambiguity in the display.
Not sure, sir.
No, nothing. See, it's all given here, right? This R unambiguous is inversely proportional to PRF.
Yes,
So
sir.
if I want this fellow to be high, definitely the PRF should be low.
Yes, sir.
So I would like to go for a lower
Low
PRF.
PRF.
Low PRF. But when you talk about the average power, this might reduce the average power, but that's not a big issue. Okay. An ambiguous display is a greater problem than lower power. So for search radars, generally we go for this sort of low PRFs in the order of 1000 hertz. Okay, 1000 to 2000 hertz. That's typical of search radars. Same thing. Here you can see that it's a pulse, means it's a pulse of RF burst. Okay, that's what it is. So it's not a digital signal. So target A, no problem, but target B is going to give an ambiguous range. Another issue is Doppler effect. This is again from your basic physics. So it goes here and then, but the relative position of this is changing because that's a relative velocity. This is stationary. This fellow is stationary, whereas this is a moving target. So a Doppler shift is going to happen to the carrier, and this Doppler shift is given by this formula. Okay, 2 times Ft into V by C. Again, you can prove it yourself very easily. This Doppler shift, and this Doppler shift, what is important is this velocity v. Okay. Now this is, we can't assume that suppose in a display, let's say the antenna is pointing at 90 degrees and target is going to come like this, head on, or it's receding in the same radial. This is called radial, okay, in radar parlance, the same radial. Uh, it's not going to happen like that. It can be that this particular point it is going tangentially, which means theta is 90 degrees. So though the aircraft is moving, there is a problem because it's 90, cos 90 is zero, you end up with zero Doppler shift, though it's a moving target. Okay. For timing, let's assume that it's coming head on or receding in the same radial. Then using this, you can calculate the Doppler shift. Now, like ambiguous range, there is something called as ambiguous Doppler. Doppler means velocity measurement. Okay. There are radars in which we can measure the velocity. So this unambiguous Doppler is given by PRF by 2. Now, instead of time, this is in frequency. So let's say this is center, PRF by 2 is this much. So up to these FDs, okay, whatever Doppler shift happens within this range, you are going to get unambiguous Doppler information or unambiguous velocity information. The moment it goes beyond that, then there is a problem. You are going to get ambiguous velocity information. So this concept of velocity is used for tracking radars, missile tracking radars. It's used for tracking radar. The previous one is for search radars. Now the question is, should I go for high PRF or low PRF? Sandita, if I want unambiguous Doppler.
I'm thinking, sir.
Yeah.
Still below.
Low, which means the range of detection is going to come down. If it is low, it's going to be in this band. So this equation says that for unambiguous Doppler, PRF should be high. It is just proportional. Okay. So I want this to be as high as possible. This width, just like a bandwidth, I want this to be as high as possible. So I would prefer a high PR. Now this is contradictory to the requirement for search radars. So that's why this is probably this is one of the basic reasons why normally we have a different search radar and a different tracking radar. So any missile system you look at, initially you'll have a search radar around 300 kilometers, whereas a tracking radar will be around 20 kilometers. So this is the basic limitation of the radar theory. Is it okay? Hmm? So all your fighter control radars fitted on fighters, if they are tracking mode, they are in tracking mode, you have to switch over to high PRF. So again, it's a compromise. Okay. Okay. Then I asked you about the pulse width. Should it be this blue one, tau one, or would you like to have tau two? And yeah, now looking at this slide, can someone tell me which is better, tau one or tau two?
So tau 1,
So why, Saru?
it's more accurate.
Yeah, or the resolution is better, right?
Yes.
If the on the PP on the display, if you are using tau 1, you can distinctly see two blips, which will tell you that two aircrafts are approaching. Whereas if you are having a very high pulse width, both will get merged and look like this, isn't it? So you lose some information if you are having a large pulse width. Of course, the average power here will be high. Here the average power will be relatively less. But we can always live with a lesser average power. So that's the reason why we can't have very high taus. There's a limitation on this. After that, another problem is that was range resolution. Okay, the previous one was range resolution. Similarly, you can have angular resolution. So that will depend on the beam width of the antenna. So would you like to have a narrow beam width or a higher beam width? And there are two targets approaching you at two different radials. Let us say one target is coming like this, the other one is coming like this. But I want to distinguish between these two targets. So would you like to have a high beam width or a lower beam width?
So like a narrower beam width.
Narrow beam width, right? Then only then on the display I'll be getting something like this. So I'll see one target here, and when the raster comes to this position, I'll see the other target. If the beam width is too high, then these two things will appear as if it's a single target. Again, we lose information. But Saurabh, what is the problem with narrow beam width?
Sir, huge side lobes.
Ah, excellent. Yeah, that's the problem. So narrow beam width means you can have side lobes like this. So this fellow actually now on the radar scope, one return will be coming from this same target, the correct target, and the other one will come from the side lobes. So you get wrong angular information. But somehow if you can suppress this, design an antenna so that side lobes are not too high, then probably this problem can be solved. Okay. So we have these problems in radars. First is range ambiguity, which means that I would like to have low PRF. If for velocity ambiguity, I would like to have high PRF. The third problem is as far as the radar is concerned, that energy just goes out into the free space and gets reflected from whatever is obstructing it. So it can come from stationary target as well as moving targets. So suppose this is the terrain and radar is kept here, and we have a hillock like this, and aircraft is approaching the radar. So on the display, what you will be seeing is this complete hillock as a blip. You will not be able to see the aircraft. So the third question is, how do we get over this problem? How do we prevent stationary targets from masking the moving targets? They literally mask them. So we'll have to find out how to do it. So that's something we'll discuss in the next class. Yeah. Any doubts on whatever I taught in today's class? Raj, how is it going on? Can you understand what I'm telling, or you're finding it difficult? Raj, can you hear me?
Yes, sir. Hello, sir.
Yeah, hello,
Uh,
hello. You are
oh,
awake, right?
yes, sir. Yes, sir. Yeah.
Uh, you're able to follow what has been covered today? Yeah, let me know. Any for the class also, any doubts you want to ask me for whatever we have covered so far on radars. Sahana,
Yes, sir.
any doubts?
So far, no, sir.
Okay. Okay then. We'll see the next class. There's something called as moving target indicator. So as the name says, it has to indicate only moving targets. So we'll see how to achieve that moving target indicator. Okay. Thanks everyone. We'll meet in the next class. Bye.